Okay, so I'll quickly try to review like the second order differential equation in general, either variable coefficient or constant coefficient. So we could look for the second order differential equation, or the things that we studied in the second order differential equation, as if we have a of x y double dash plus b of x y dash plus c of x y equal f of x, right? So this is the general form of a second order differential equation. And we classified this, or we done this in two steps, actually, two big steps. The first step was we took the constant coefficient case. The constant coefficient case, which is A, B, and C are constants. Which means this would be A y double dash plus B y dash plus C y equal f of x. And then in this case, we said that we are looking for the y general, which is yc plus yb. This is the general case, but assuming that A, B, and C are constants. Now, in the YC, for YC, we normally build something called the characteristic equation, which is YC is, corresponds for the solution of the homogeneous part. YB corresponds for the solution of the particular part, which is the f of x. So for the YC, we build the characteristic equation A r squared plus PR plus C equals 0. And then we solve this second order algebraic equation for R1 and R2. And we expecting here to get one of these three cases, which is R1 is not equal R2, two real different. R1 equal R2, so two real equal, or R1 and R2 are complex, which is alpha plus and minus I beta. So this is the three cases for this second order algebraic equation. For in this case, we say that the YC is C1 e to the power R1x plus C2 e to the power R2x, as if we found two y's that satisfy this differential equation, and we add them, like this is y1, this is y2, and we multiply C1 times y1, C2 times y2, which is the superposition principle. In case of the R equal, we almost do the same, but we multiply by x to avoid the linearly dependent. So C1 e to the power Rx plus C2x e to the power Rx. And in this case, this is y1 and this is y2, including the x. In the third case, it's actually the same, but after some manipulation, we reach that we can write YC as e to the power alpha x times C1 cosine beta x plus C2 sine beta x. This is alpha, the real part. This is beta, the number that is multiplied with I. We put the beta here, we put the alpha here. So this is when the second order differential equation, the homogeneous part of it, when it's constant coefficient. And I guess this part is easy now because it's just very straightforward. And then for the YB, we studied two different methods in order to find the YB. One method is called undetermined coefficient, and the other method is called variation of parameter. for the undetermined coefficient, it solves, or we studied the undetermined coefficient for specific families of functions, not for all functions. I'm talking about this function here. So for the undetermined coefficient, we studied 3 different families. It's either a polynomial, exponential, or sine alpha x, cosine alpha x, or even the combination between them. In this case, we in the YB, we always assume the YB. We always assume either in undetermined coefficient or in variation of parameter. But here in the undetermined coefficient, we assume it to be similar to the f of x. So if you have f of x as a polynomial, you assume YB to be a polynomial. If f of x is exponential, then you assume your YB to be also an exponential. So polynomial from the same degree. Here, YB is a cosine alpha x plus b sine alpha x, regardless if you have sine alone, cosine alone, or sine plus or minus cosine. It's always like that. So, and then we added a 4th case. It's not really a 4th case, it's really just a combination of these cases, which is if you have, and we divided this to have kind of 2 streams. If they are added, then we add 2YB1 plus YB2, and then we divide the problem as 2 separate problems. Now I'm talking about the YB part. The YC part, we already done with it. If they are multiplied, if like you have 2 of these families, or 2 functions of this family, 2 members of these families that are multiplied, we multiply the both YBs. And I guess this should be okay by now, because we done the quiz 2 and things were okay, I guess. And then we did the variation of parameter, which is actually very powerful method that solves for all second order differential equations. In fact, it solves for all differential equations, not only second order differential equations. It solves for all higher order differential equations as well. But things become quite complicated when we go beyond the second order. So we focused on the second order case. The variation of parameter method, you always assume the YB is U1 Y1 plus U2 Y2. For the people who just arrived, we're reviewing all the second order, the landscape in the second order differential equation in general. So the YB in the variation of parameter always is U1 Y1, U2 Y2. What is Y1 and Y2? Those are, we get them from the YC. So this one here, this one here, this one here, this one here. In this case, YC, you should write this as C1 e to the power alpha x cosine beta x plus C2 e to the power alpha x sine beta x. And this, all of this will be Y1, all of this will be Y2. So Y1 and Y2, in the YB, in case of variation of parameter, we use the Y1 and Y2 that are coming from the YC. So what's left is U1 and U2. How are we gonna get U1 and U2? Very simple. We start with, or we say U1 equal negative integration 1 over A of x. Let's write it this way now, from now, because we know that we're gonna need this later. 1 over W, and then Y2 f of x dx. U2 equal integration without the minus 1 over a of x 1 over w y1 f of x dx. Okay, let's see. Do we have all of this in order to find the u1 and u2? I guess yes, we do. How is that? The a of x is whatever multiplied with y double dash. So this part here. It's just a because a of x is just a in this case. But this works for all second order differential equation, either constant coefficient or variable coefficient. So we should just write it as a of x. So we know what is a of x in this case. W, I'm going to write it soon. Y2 is coming from the YC. Okay, good. All right. I am in the record, so I don't want to say bad words. For Microsoft, I mean. I love Microsoft, of course. Everyone do. Yeah. All right. So the y1 and y2. So خلي بالك. Here in u1 we use y2. In u2 we use y1, and the y1, the y2 and y1 we get them from the yc. So those we know where to get these. The f of x is your forcing function in your differential equation. That's the forcing function that's will be given in here, which is this part. So we have everything except the w. The w is y1, y2, y1 dash, y2 dash, which is y1, y2 dash minus y2, y1 dash. And the procedure starts as follow. Number one, find yc. That's, I mean, the procedure for variation of parameter in general. Find yc, and then get y1 and y2. That's, we get them from the yc, right? Or I might give you y1 and y2, or might be given in the problem. So we need to get y1 and y2. So that's the first step. Second step is find w, which is again y1, y2 dash minus y2, y1 dash. Number three, find u1, find u2 from these forms, and then construct your yb, which is u1, y1 plus u2, y2. Okay, this is all what we did in the second order differential equation in case when it is homogeneous. In case it's very constant coefficient, homogeneous or non-homogeneous, in case it's constant coefficient. Constant coefficient means these numbers are constant. Then we moved, again, we said we started, or this is our task generally in that chapter completely, like solving the second order differential equation in a generalized form. And then we divided it to two big parts. The first part, which is constant coefficient, and we done this. Now the second part is variable coefficient. When we have a of x, b of x, c of x are variables. Like you see x's times y double dash, and x's times y dash, and x's times the y. And we said this case is not very easy, like to find like a generalized solution in one shot. So I'm gonna start here as again a of x, y double dash, plus b of x, y dash, plus c of x, y equal f of x. But now I'm assuming that a of x, b of x, c of x are functions. I mean functions in x. They have x's. And we said for this case, we're gonna also look at it as kind of two branches or two classes. Don't worry about the YB because YB is variation of parameter in this case. So how we're gonna do it? Exactly as we did it here. You need to have Y1 and Y2, build the W, find U1 and U2, build the YB. This is for all second order differential equation. You can use that method. Either variable coefficient or constant coefficient. So we are not really worried about the YB. Why? Because we can use variation of parameter always. Well, yeah, that comes with a little bit of risk because of the integrations. But our problem now is, what is the YC of this problem? What is the YC when we have variable coefficient? That's the main target that we're looking for now. And we said we're going to look into this in two different classes of systems. The first class is that something called Euler-Cauchy equation or Cauchy-Euler equation. Cauchy-Euler is like a special case of this generalized case. The good thing about it, it does not require too much information about the YC if it is written in the Euler in Cauchy-Euler. What is the Cauchy-Euler? Cauchy-Euler is that when a of x, or of all these functions, is just ax squared. So a x squared y double dash plus bx y dash plus c y equal f of x. In this case, we call it Cauchy-Euler. What is specific about Cauchy-Euler is that when you have double dash, you have x squared. When you have one dash, you have x. When there is no dashes, there's no x's. We could also, or we said there is a bit of a generalized form of Cauchy-Euler or Euler-Cauchy as a x minus x naught y double dash square here plus b x minus x node y dash plus c y equal f of x. We could use that form as well as a little bit of a generalization of Euler-Cauchy, and for this specific case, we let z equal x minus x node, and then we turn this differential equation as a differential equation in z by just doing dz equal dx. So this differential equation can be written as a z square y double dash plus b z y dash plus cy equal f of x. In fact, here it will be f of z. But we could just solve the homogeneous part because we are not in a problem with the YB. Our main issue is with the YC, and then we could solve this as Euler-Cauchy. How is yes? Yes, it is a number. It is a number. It could be positive or negative. Okay, but it's a number. The main important point is that this is exactly as this. The structure of this part is the same structure of this part. The only difference is here is square, here is there's no square. Azim. How are we gonna solve the Euler-Cauchy, or how Euler-Cauchy is solved? That's not very a big problem because it's very similar to the constant coefficient case. How is that? We build the characteristic equation as well, which is in this case ar squared plus b minus a r plus c equals 0. That's so the first difference that we can see is that part, right? So that's the characteristic equation of if you have a Cauchy-Euler equation. Okay, and then we solve for R1 and R2. That's very similar again. And we're gonna get R1 and R2, obviously, since it is algebraic equation, second order algebraic equation, it must have two roots. Those two roots, they are either two real different or real equal or complex. Very similar to the previous one. Here, the YC also not very different, but the base here is x to the power r. So that's the assumption that Euler-Cauchy solves their problem. They assume that y equal x to the power r. And then they generated this they generated this characteristic equation. Well, okay, so here the YC will be C1 x to the power R1 plus C2 x to the power R2. Here YC will be C1 x to the power R plus C2 x to the power R. We multiply by ln x. Here YC will be x to the power R, sorry, actually x to the power alpha, C1 cosine beta ln x plus C2 sine beta ln x. And that's it. That's your YC. This is YC in the case of Euler-Cauchy, the first class of the variable coefficient second order differential equation. Okay? Is the map is clear now? Or which part we're doing at the moment? Or reviewing? And then when we're done with this, we said that, okay, there is the last thing that we could also use, or that the last thing that we are going to study. Obviously, there is other different methods for solving this generalized equation. Actually, one of the most powerful method that it's used is called series solutions for differential equations. That's a very, very powerful method, and actually that's the one it's used in real life in most of the cases, but it's also, it does not give an analytical solution in most of the cases. It gives numerical solution. But here we're doing the analytical parts. So the other method that, or the other class that we are going to study are a class of system that where we could use a method that's called reduction of order. And from the method, it suggests that we are going to reduce the order of this second order differential equation to something lower, which is first order differential equation. Is that something good? Yes, because we already done a first order differential equation and we know how to deal with them. Particularly that the methods or the cases that we are going to study, they all reduced to linear first order differential equation, which is something actually very well understood and very well structured in terms of the solution. Okay. So the reduction of order method, we said we're gonna look into it in kind of two cases. Case one and case two. Case one, where we can solve the second order differential equation when we do not have constraints on A of x and B of x, is as follows. When you have A of x, any A of x in this case, y double dash, plus any B of x, y dash, equal f of x. What's left here, or what's not presented, is the y. Here, case one, you can easily say that C of x equals 0. You don't have that last term. If we have this, then things become very easy and very intuitive as well, which is the solution is very robust as well, because you only need to reduce this into a linear first order differential equation. And once you reduce this to a linear first order differential equation, you solve it as linear, and then there is another small integration you do after to get the y. How are we going to do that? We just pick another variable. I guess we agreed to pick v, right? V. Yeah. V equal y dash. It's just kind of, instead of taking y double dash, so you're going to reduce the order by 1. So v equal y dash. That means v dash equal y double dash. And then we take this, substitute in this differential equation that does not have a y. We cannot do this in the case of y, because what is y in this case? It would be integration of v, which is something we don't know, because we don't know v even. So here, This only works when C of x equals 0, which means the y term is not there. So the generated or the new transformed differential equation will be a of x v dash plus b of x v equal f of x. And then we can go ahead and divide by a of x to generate a new differential equation, which is v dash equal, plus b of x over a of x, v equal f of x over a of x. And this looks something familiar to us, which is linear first order differential equation. We just need to write it as dv by dx plus b of x may be v equal q of x, where this is b of x and this is q of x. And this is a linear first order differential equation, which, assuming we know the solution, because we did linear first order differential equation. In fact, the solution is very easy because it's just two steps. We find the integration factor, which is mu equal e to the power integration b of x dx. And then we said that the v equal 1 over mu, or you could multiply mu times v and then divide. It's both the same. Equal integration mu times q dx plus a constant. And please call this a constant C1. And one important fact is this mu, 1 over mu, multiplied with everything, including the constant. Okay? Don't forget that part. Once you get the v, I mean, the v was just a variable that we introduced. We were not interested in finding the v itself. The v was here to help us in finding the solution of this second order differential equation, which is in y. Which means, let's go back. Okay. We were just, for the time being, letting v equal y dash. And we got v. So we can go back and say, okay, we know that y dash equal v. Then let's integrate both sides. Then that means this will give us y, and this will give us integration, the v that you just got from here, dx, plus another constant, because we're doing another integration. And this would be your y general, in fact. We'll give you yc plus yb. And that's why you're going to see two constants plus a free term, which is the accommodate for the yb. Okay, so this case is not, you should not miss this case. This particular case is very easy. All what you do in the second order part is just this reduction here. And then it becomes first order. And you guys are good in the first order. Right? Yes. No. If you took this f of x, so you don't need to. Euler-Cauchy. Yes. I didn't say that. So I thought that I did in above. So here, yb is always variation of parameter in that part, in the Euler-Cauchy. That's because Euler-Cauchy were just to find the yc, because it was the problem. We agreed that here, actually, we don't have a problem with the yb. Our problem is was the yc. So Euler-Cauchy helped us in finding the yc. Yes. In this case, if we did it as I did it here, no, because we got the yb for free. But also, we could have just focused on this part, ignoring f of x for the moment, solving all of this problem. This will be 0. This will be 0. Q will be 0. So you're gonna end getting only y2. And then go back and do variation of parameter if you wish. Okay. Yeah, this gives you, because we're doing YB internally while we're doing that. Okay. But because it can be reduced to first order differential equation, you can get YB quicker here. You don't need to find W, U1 and U2 and all of that. Okay. So, and I recommend this because it's shorter and it's more intuitive actually. But obviously you can, here says, okay, no, I'm gonna ignore looking to this part for the moment, solve this as just a homogeneous part, this part here, finding, do all of this, you'll find everything goes exactly the same, but Q of X will be 0. And here this part will not be there. So you're gonna find V, it will be just Y2, or actually Y1 and Y2. Finding Y1 from here, and then you integrate, you find the Y2. That's why you're gonna get the two constants. And then go back to look for your non-homogeneous part, which is this part, and use variation of parameter if you wish. Okay? But again, that's longer than what I did. Is this part is clear? Yes. So this will be a function of X. V will be just a lot of X's. Okay, because we generated it from solving this differential equation, which is C here. All these are just X's. Okay. And then we came to the last part that we covered in the second order differential equation, which is case 2, which is again like kind of the most generic or generalized form that we reached. So case 2 in reduction of order, and this is what we did the last 2 lectures. So reduction of order, case 2. Case 2, I'm just calling it as, I mean, there's no really case 1 and case 2 in the textbook. I'm just calling it this to make things easier. But if you go to the textbooks, a lot of textbooks actually, they don't mention this case at all. They only do this and they include case 1 inside, which make it a bit difficult actually. So dividing them now, it's easier, I guess. Okay, just in case you are following one textbook or something. So case 2 is again now the generalized A of X, any of X, Y double dash, plus any B of X, Y dash, and also in the present of X of C of X, Y equal F of X. Well, that's like the big guy. Do we have a generalized solution? No. We said that in the beginning. So what case 2 do is that it says if you have at least Y1, at least part of the YC. Remember the YC always Y1 and Y2, right? C1 times Y1, C2 times Y2. If you have one of them, let's call it Y1, then we can continue doing the rest of the solution, which is Y2 and YB, because we know that basically the solution of this differential equation is Y general, which is YB plus YC, or YB plus C1 Y1 plus C2 Y2. That's the expected solution. If he can, or if the problem, or if we can know some information about one of the solutions and the YC, then we can easily go ahead and find the Y2 and also find the YB. Okay, so that's what case 2 does. So in case 2, you will always be given some information, or you will be given Y1, or maybe Y1 and Y2. That's also could be, actually that's easier, because if he's giving us Y1 and Y2, what's left? YB. YB is, we know, it's just variation of parameter. Yes. Yeah, Euler-Cauchy is a of x and b of x are ax squared, and this is bx. This is just x squared. This is a generalized function of x. This is just ax squared. Okay? We made it clear here. We took a branch of this, the generalized form, and we said it's ax squared, bx, and c. Okay? All right. So how are we going to get y2? I mean, again, our problem is y2 really, because always you can solve the homogeneous part, and then for the yb use variation of parameter. There is a method. I mean, it's yes, it requires some derivation, but there is a method, which is by now I guess we know how to do it, which is the variation of parameter. But our main problem is that what is y2? Well, as we did in several occasions, if you don't know the solution, just assume it and try to re-engineer it. I mean, like do some reverse engineering to that assumed solution to make it look like a solution, which is in this case, we're gonna assume that the y equal u of x, a function of x times y1. Okay, and I guess we talked about like why this is a proposed solution when we first did that. So basically, you just, this is the only piece of information that you need as a new piece of information. Everything else is known. How is that? Again, now we assume that this is a solution. What that mean? It satisfies the equation. That's, again, we knew that. We used this several times. So it satisfies the equation means that I can find y dash, y dash, y double dash. In this case will be u dash y1 plus u y1 dash. This will be u double dash y plus u dash y dash plus u dash y dash plus u y double dash. Those are two functions multiplied together because u is a function of an x. So you have y dash, we have y double dash. Take all those three, substitute in the equation that you're trying to solve, which is this one here. Just make it a bit cleaner. Substitute in this, because you know y1, I'm giving you y1, or y1 is given. So you can easily do that. Substitute. You're gonna get a very long differential equation, but in u, y will disappear because, I mean, we substituting the y. But what about y1? y1 is given. Like all these are just the y1 that was given to you. So again, it's a function of x. So after substituting with these in the original equation that you are solving, you're gonna end up with some function. Let's call it I'm running out of b of x u double dash, or b0 of x u double dash plus b of x, or b1 of x u dash equal f of x. You must reach this point. I mean, by must, saying that it will always, the u will disappear. You will not have c of x. So you will have only some x's times u double dash, some x's times u dash. What about the other term? It will disappear. I mean, you will find things multiplied with u, but all this has always to become 0. You don't make it 0. It will come to be 0. If it didn't, then you made something wrong. Okay? And then we solved few problems on this in this particular case, and it was always it goes to 0. All right, since we have this equation, is this something new for us? This is case 1. This is a second order differential equation that has no y in here. There is no u, or c of x equals 0. Then we can use what we did here. What we did in case 1, which is assuming a new variable. So we're gonna come here and assuming v again equal u dash, v dash equal u double dash, and then take this, substitute there. You're gonna end up with a function b0 of x, u double dash, v dash plus b1 of x, v equal f of x. And then you know what to do here. You're gonna get the v. Once you get the v, you're gonna go back to get the u, which is u equal integration of v dx plus a constant. In fact, that will be constant 2 because you're gonna get a 1 constant here. Once you get the u, what was the u? It was part of the y because y1. And the good thing here is that similar to case 1, we got yb for free, right? Here as well, we're getting yb for free. You didn't need to go back and do variation of parameter unless you came at any point here and you said, okay, let me decide that I'm gonna ignore this part, ignore the forcing function for the moment, solve for the homogeneous case, and then go back and find yb. You can do that. You can always do that. Okay? yb is just if you are doing reduction of order, either case 1 or case 2, you can always get it for free or leave it for now and then come back and use variation of parameter. Okay? In fact, this summarizes everything that we did in this, like in the last four weeks, I guess, or 3 weeks. I don't know. And like in the second order differential equation. I mean, I didn't solve any problem, but like this should be clear to you by now before the midterm, please. Like these methods, and you should have your own map, your own like piece of paper where you write or like draw this map in front of yourself, because deciding which problem is this is actually the important question in the exam. Okay? Is that any questions so far? Yes. Yes, exactly. You need to do that. I mean, we're doing all of this to get the y2. But while we're doing that, we got the YB for free. But yes, if you are given y1 and y2, then that's a lucky day, because you don't need to do all of that YC part. You just need to go and do the variation parameter. So for any problem, if you are given y1 and y2, which is the fundamental set of solutions, it's called the fundamental set of solutions. I might tell you the fundamental set of solutions is e to the power x and e to the power 2x. That means this is y1 and this is y2. It's called the fundamental set of solution. I guess there is some questions in the homework that says exactly that. Once you have the fundamental set of solutions, then you know what is yc. But what you need is yb. So you're gonna start immediately getting w, y1, y2, y1 dash, y2 dash, and then getting u1, getting u2, then your yb. You know how to do it. Sorry? A? Yes, I'll be giving you that. That's a very, very important question. I'm not giving you only the fundamental set of solutions without the differential equation. I'll be giving the differential equation to get the f of x as well. Like I'll be giving you, for example, I don't know. I mean, something, I don't know if this is the fundamental set of solution or not, but it will be a مثلا x cube y double dash plus 2xy dash minus y equal x squared plus 2x, something like that. And I'm giving you y1 and y2. So you don't need to worry about the yc. All what you need to worry is the yb. yb requires what? Requires y1 and y2 given to you. Requires a of x, it's here. Requires f of x is here. Then you are good to go. Yes. Yeah, you will always be given y1. I mean, y1 and y2, whatever you call y1, I can call it y2. It's just two fundamental set of solutions. Okay? So if I'm giving you only y1, then you're going to do what I did here. You assume that the y will be u times y1, and then start the derivation. You mean y1? Yes, yes, yes. Don't say it this way. Don't say when I see that, do that. That's if you're programming a machine. It's just like the reduction of order method. We cannot use it for the general case unless we have some information about the YC. What is that information? Is Y1. Okay. In this case, we're gonna generate the rest of the solutions based on this information that we are given. Okay. Because I might be giving you Y1 and Y2. That's not a reduction of order anymore. Because you don't need the reduction of order to find Y2. It's just you need the YB. So it's a variational parameter, really. It's really a variational parameter. So if you are given y1 and y2, that's not a reduction of order. It's just variational parameter, right? Because you need only the yb. Okay? Any questions? Any more questions? Please. It's yes. Obviously, we can. Let me get one question, because doing the question, I can like draw any question, but we will stuck in the integration. So I don't want to do that. Well, let's solve this one. Hopefully, we will be okay. So a typical exam question could be something like this. X, y double dash, plus 2 minus 2x, y dash, plus x minus 2, y, equal e to the power 2x. And here he says y1 equal e to the power x. And he says find the general solution of this differential equation. All right. What is like the way that we going to organize our approach here, or our thinking in solving this problem? Yeah, let's say out loud, what is this differential equation that we are solving? This is a second order, so we know we are not in the first order mode, we are in the second order mode. So second order mode activated, because we have 2 double dash. Then is it variable coefficient or constant coefficient? Variable coefficient. Why? Because we can see x is everywhere. So it's a variable coefficient. So variable coefficient, we have two things to think about. Is it Cauchy-Euler or reduction of order? It's not x squared, it's not x here, there is x's here. So this is certainly not Cauchy-Euler. Okay? And also he's giving us y1. So it's more evident that this is reduction of order. Sorry? Case 2, exactly. Because there is y. Well, since he's giving us some information about the YC, this is, so typically we are looking for Y general, which supposed to be YB plus C1 Y1 plus C2 Y2, where we call this YC, right? That's our aim. That's what we're looking for. And that's what we are expecting to get. What we have at the moment, we already given Y1. So that's good. So let's start to do it step by step. But we know that this method, or we could use reduction of order method to actually find all of that at one point. Like the YB, we will be trying to get the Y2, but we will be given YB for free because we are going to consider this with us, since it's not really adding anything to the complication unless the last step, which is linear first order differential equation, and we know what to do in there. So that's my approach. Or you could say, no, I need to do things separately. I will just ignore this part here, solve for my Y2 first, using reduction of order as well. And then once I have my Y1 and Y2, I look to them, okay, they're nice, they're good, put them aside. Let's now go use variation of parameter to get YB. You could do that. But actually, we are not that, we don't have that free of a time. So let's get YB while we're doing the process. So what you should do here is that say, okay, our Y equal U Y1, which is U e to the power X. Okay, so that's where this from. It's the Y1 that he's giving me. And then Y dash, because since this is a solution, it should satisfy the differential equation. So Y dash will be U e to the power X plus U dash e to the power X as well, right? Because it's the derivative e to the power X is e to the power X. Y double dash U e to the power X plus U dash e to the power X plus U dash e to the power X plus U double dash e to the power X. I love e to the power X. It's just a good function. Now we have our 3y, y dash, y double dash. Take these and go back and substitute in the differential equation, which is the differential equation that we're solving here. All what we need is to just remove y double dash, put its value, remove y dash, put its value, remove y, put its value. Please make sure that you wrote the signs correct. Please make sure that you done the multiplication correct. That's all what I need from you. This is just high school algebra. Okay? But let me first make sure that I wrote the question correct. Okay. Yes. X plus everything, I guess, is okay. So now we put X here, and then the y double dash. I always actually like to do that this way. Plus what 2 minus 2x, just to make sure that I put the brackets, because the brackets are the devil here. So let's make sure that we put them. Plus x minus 2 that's e to the power 2x, right? Now let's plug every term. What was y double dash? I guess we can add those two terms, right? Y u dash e to the power x. Yes. كده ان انا لو زوم ان الايكويشن طويله شويه. طيب خلينا يعني احنا عارفين احنا what we are doing in here. So I will substitute y double dash here, which is I can add those two parts. So this will be u e to the power x plus 2 u dash e to the power x plus u double dash e to the power x. Right? Let me write y dash in a different color. Y dash is just u e to the power x plus u dash e to the power x. Then what is our y? actually u to the power x, right? And now we will need to multiply this x inside. So this will be, well, again, annotation that will always appear when you have e to the power x as your y1, that you will find e to the power x is everywhere here, right? So we can somehow divide by e to the power x because it's multiplied by every term to just make things a little bit shorter. That's all. So here I can say that x, why this pen is behaving weird, x u plus 2x u dash plus x u double dash plus, now I need to be a bit careful, 2u plus 2u dash minus 2xu minus 2xu dash, right? Okay, plus xu minus 2u equal e to the power 2x over e to the power x. That's good. Now, again, see all the y's disappeared. And we know that we are expecting a second order differential equation in the u, and the u part itself should not be there. That's our anticipation. So something should be, yeah, we can. Plus, I don't know why my pen has some delay. حتى القلم زهق من كتر الكتابة. Okay. Let's carefully look for the coefficient of u double dash. I guess u double dash appears only once. That's not a problem. U dash 2x plus 2 minus 2x. That's it, right? Great. The u hopefully this part should be equal to 0. I did not make it 0. It should appear as 0 after we do that, hopefully. Yes. So x and minus 2x and plus x, all the x's will go. Plus 2 and minus 2 will go. That's okay. That means a very good sign that we're doing things correct. So our problem becomes x u double dash plus, and I guess this 2x with this 2x, 2u dash equal e to the power x. Very simple, very easy, very elegant second order differential equation that it's without the u here. I guess the solution should be easy from here, because we know that we're going to reduce this using v equal u dash, v dash equal u double dash, substitute x v dash plus 2v equal e to the power x, divide by x, v dash equal 2 over x, v equal e to the power x over x. Please don't forget to divide everything by x here. Don't get really excited and it says, okay, I know what I'm doing here, and then you forget this x. Okay, that happened. And this is actually plus. So this is the first order differential equation that it's linear, right? So mu equal e to the power integration 2 over x dx, which is e to the power 2 ln x, which is Yes, ln x squared, which is x squared in the end. Right? This part is important. So we have mu, then we say our v equal 1 over x squared times integration x squared times e to the power x over x dx plus a constant, right? Oh, C1. Then, which is 1 over x squared. Don't get this inside until you finish the integration. You have to finish the integration first. This will be x e to the power x integration dx plus C1. This is integration by part. 1 over x. After the integration will be x e to the power x minus e to the power x plus C1. I mean, I've done the integration by part in my head. Yes. So here we just let this x squared get inside. One over x e to the power x minus 1 over x squared e to the power x plus C2 over x squared. Okay, that's the v. What was the v? The v, sorry? V1. Why it was C2? Because I got an email here, a notification of email says, please look to the point number 2. That's why the 2 just came here. All right, so that's the v. So we needed the v. Let's just go back. We were doing the v to get the u. So the u dash equal v, u equal integration of the dx. And you need to integrate that. Sorry? Yeah, plus a constant, C2 in this time. So you integrate all of this, which is not very difficult. I mean, integration by part in the 3 cases. Yeah. And then you after you get the u, you just need to say that your y is the u after you integrate that times y1. What is y1? E to the power x. You're gonna get three main components. One component which has C1, the other component which has C2, the last component which is something that appear from here, that's YB, that's C1 and C2. Those are responsible for YC. Okay. Yeah, it will be there by default, actually. Okay. They will be a formula sheet, but that does not mean the integration will be there. I mean, integration by part is not there. You have to know what's integration by part. But I'm giving you a form that has all the basic rules of integrations. Okay. Any more questions? Is that okay? More questions? No? Let's just stop the recording. Yes. Let me just first see why it's not leaving. Please, Mr. Microsoft. Okay, let's stop. Microsoft Drama. I guess if I just hang it out,